Yeah, good afternoon, students. So, in the previous class, we had a discussion on the pipelining concept. Now, today, the classroom discussion topic is on data dependencies and memory delays. How do we compute that? So, now I would like to share my screen. So, the topic for discussion is the data dependencies and memory delays. The lecture objectives are this session will develop the students' knowledge on the different issues related to data dependencies as well as the memory delays. So, actually, we had a discussion on the pipelined execution of multiple instructions. So, when we are executing the instructions in a pipelined manner, we are able to achieve the performance in a better way. So, the data dependency means that whenever one particular instruction is executing, the output written by that particular instruction act as an input to the next instruction. That means the first instruction output data is required as an input to the second instruction. That means the second instruction is depending on the output written by the first instruction. That is what we are calling it as a data dependency. For example, you take this instruction add r2 comma r3 comma hash 100. That means contents of r3 and immediate value 100 will be added and the result will be stored in r2. Coming to the second instruction, when we are executing the second instruction, subtract instruction, so we are trying to subtract r2 value, contents of r2 and the immediate value 30, we are subtracting it and storing the result into r9. So that means to perform the computation in the subtract instruction, R2 register value should be available, then only this instruction can be executed. So that means it has to wait until the first instruction completes its execution. So it has to wait, then only the data available in the R2 register. Fine. So that is what we are calling it as a dependency, data dependency. So if you are considering this first clock cycle, so during this first clock cycle, the first instruction add instruction will be fetched. Second clock cycle, during that second clock cycle, the add instruction will be decoded, and in a pipelined manner, the first second instruction subtract instruction is fetched into the memory, fetched from the memory. Fine. Now during this clock cycle 3, so the instruction 1 is performing the computation, content of R3 and 100 value is added, and during this clock cycle 3, so this instruction, second instruction will be decoding. So that means the second instruction has to be delayed until the first instruction, add instruction, will write the output into this R2 register. Fine. So that means this clock cycle 4 and clock cycle 5. After this clock cycle 5, then only the value is available in the R2 register. So till that, okay, so the second instruction, subtract instruction, has to be delayed. So then during the clock cycle 7, the computation can be performed by the second instruction, because once the first instruction is performing the right operation during the clock cycle 5, after this clock cycle 5, so the result is available in the R2 register, then the second instruction, subtract instruction, can perform this subtract operation. Then clock cycle 8, memory operand values operation can be done, and then write instruction or write operation can be done. Fine. So that is what we are seeing here. The destination register R2 for the add instruction is a source register for the subtract instruction. So there is a data dependency between these two instructions because register R2 carries data from the first instruction to the second instruction. Fine. This is what the dependency we are calling it as data dependency. So the subtract instruction is stalled for 3 cycles to delay. So it should be stalled for 3 cycles. Okay. So for cycles to delay reading register R2 until cycle 6 when the new value becomes available. Fine. So the control circuit must first recognize the data dependency when it decodes the subtract instruction in clock cycle 3. Okay, during this clock cycle 3 when the subtract instruction is decoded, during that the control circuit or the control unit has to identify so that it requires the data from the first instruction. So there must be a delay so that by comparing its source register identifier from the interstage buffer B1 with the destination register identifier of the add instruction that is held in the interstage register buffer B2. So it can able to do that. So then the subtract instruction must be held in the interstage buffer B1 during cycles 3 to 5. So the add instruction proceeds through the remaining pipeline stages. So in cycles 3 to 5, as the add instruction moves ahead, control signals can be set in interstage buffer B2 for an implicit no operation instruction. So during this clock cycle 4, 5, 6, so the second instruction has to perform no operation. So that indicates that it does not modify the memory or the register file. So each NOP creates one clock cycle of idle time. So this is one clock cycle is created as an idle. So and this is another clock cycle that is created an idle. So this is an idle clock cycle time. This is an idle clock cycle time, and this is an idle clock cycle time. This is what NOP we are calling it as. Fine. So this is what we are going to call it as a bubble. A empty clock cycle is created here as it passes through the compute memory and the write stages to the end of the pipeline. So to overcome this, what we are calling here is that we are making use of a concept call it as operand forwarding concept. So we are making use of this what we are calling it as here. The desired value is available at the end of cycle 3. Okay, at the end of the cycle 3 the desired value is available when the ALU completes the operation for the add instruction. Fine. So once this compute uh, operation is carried out during the clock cycle 3, now the result is available in the ALU. So what we will do here is that we are making use of a concept of operand forwarding we are using here. So this value is loaded into the register RZ. The arithmetic logic unit output is written into the RZ register, which is a part of interstage buffer B3. So rather than stall the subtract instruction, so the hardware can forward the value from register RZ to where it is needed in clock cycle 4. So which is the ALU input. So that is what we are calling it as. This is a flow diagram here. Once the operation is carried out by ALU, the output of that ALU is written into RZ, which is a buffer register, temporary buffer register. This RZ value is forwarded again as an input because the second instruction may requires that as an input. So we are giving it as the mux b we are giving and as well as the mux a we are giving. So whether it is requiring the input the output of that first instruction is requiring as an input to the second instruction. So that is mux a will have this the selection line 1 and mux b is introduced with the selection line 2. So for this we are going to make use of this what we are calling it as forwarding of the operand. So then how do we handle these data dependencies in the software? So software we are making use of this what we are calling it as no operation we are introducing here NOP. So three holes are going to be created once the first instruction add instruction is executing. So requiring the compiler to identify dependencies, and based on that it has to insert NOP instructions, which simplifies the hardware implementation of the pipeline. However, the code size may increase and the execution time is not reduced as it would be with operand forwarding. So here the clock cycles, if you take it as here, what is happening here is that clock cycle, during clock cycle 1, so add instruction will be fetched, and during clock cycle 2, so the no operation is performed here. Okay, so during clock cycle 3 no operation is performed, and during clock cycle 4 also no operation is performed. Then during clock cycle 4 the instruction add instruction will be in what we are calling it as it is in memory write operation. Now during clock cycle 5, so what we are doing here is that the instruction is subtract instruction is going to be executed during this clock cycle 5. It starts fetching of that instruction, and then decoding, and then computation, and then memory write, and then memory operands, and then write the result. So here the total number of clock cycles required here is again 9, so which is not reduced as similar to this data dependencies what we have seen operand forwarding mechanism. So the number of clock cycles is same. Fine. So this is what we are making use of this software we are using here by introducing no operations. Fine. So now the reflections part 1 here, what is meant by operand forwarding? Any students? So now coming to the memory delays. So this what we are calling it as the memory delays here. If you take the clock cycles, this 1 2 3 4 and so on. So this is a instruction ij, which is a load r2 comma r3. So if you take this this is ij plus 1 instruction, ij plus 2 instruction. If you take that, so ij instruction will be here during clock cycle 1 it will be fetched, and during clock cycle 2 the first instruction ij instruction goes to decoding phase, but ij plus 1 will be fetched. During clock cycle 3 the first instruction ij will be in computation stage, and then this will be decoding stage ij plus 1, and ij plus 2 will be in fetch phase. Find this during clock cycle 3. But during clock cycle 4, what is happening here is that it is a memory operation, it is performing that ij instruction, and ij plus 1 will goes to this what we are calling it as computation. Ij plus 2 will enter into the decoding. Now what we are doing here is that we are making a delay of 2 clock cycles we are delaying here, fifth and sixth clock cycle we are delaying here. So this is what we are calling it as a delay, memory delay operation. Here we are doing that. Okay, so then after that in sixth what we are doing here is that we are performing the write operation, and in eighth the second instruction ij plus 1 is performing the write, and in ninth clock cycle ij plus 2 is performing the write operation. Fine. So load instruction may require more than one clock cycle to obtain its operand from memory. So this may occur because the requested instruction or data are not found in the cache, resulting in a cache miss. So we are making use of this memory delay. So what is happening here is that we are performing this operation here in this particular cycle. Assume that the data for the load instruction is found in the cache, requiring only one cycle to access the operand. Fine. So the destination register R2 for the load instruction is a source register for the subtract instruction. So operand forwarding cannot be done because the data read from memory. In this case, cache are not available until they are loaded into register RY at the beginning of clock cycle 5. So therefore, the subtract instruction must be stalled for one clock cycle to delay the ALU operation. So that is the reason here the subtract operation is delayed here, stalled for one clock cycle. The memory operand which is now in register RY can be forwarded to the ALU input in cycle 5. So the compiler can eliminate the one cycle stall for this type of data dependency by reordering instructions to insert a useful instruction between the load instruction and the instruction that depends on the data read from the memory. So the inserted instruction fills the bubble that would otherwise be created. So if a useful instruction cannot be found by the compiler, then the hardware introduces the one cycle stall automatically. So if the processor hardware does not deal with dependencies, then the compiler must insert an explicit no operation instruction. NOP instruction has to be inserted explicitly by the compiler. Fine. So now coming to the reflections part 2, it's a time for the question here now. So what is a memory delay? So coming to this is a lecture level practice problem. Now calculate the number of cycles required for execution of the following instructions. So by considering the data dependencies, this is the I1, instruction 1 and instruction 2. So there is a data dependency is there here because R4 which is used here, okay, as an output of this first instruction. So how many number of clock cycles are required for execution of these following two instructions considering the data dependency? Fine. This is the lecture level practice problem. Please try to solve it. So the outcome of today's classroom discussion topic is that after completion of this session, you will be able to compute the number of clock cycles required to execute the given instructions using data dependencies as well as estimate the memory delay time. Okay. So thank you very much.